Hello and welcome to our workshop Smart Electrodes, Smart Metallic and Semiconductor Materials Synthesis, Characterization, Application and Challenges in the framework of International Conference on Nanomaterial Science and Mechanical Engineering, University of Aveiro, Portugal. I would like to thank you, organizers from University of Aveiro, for this possibility to give our presentation and to present our project and our workshop. So I'll give briefly the introduction about project and also about the development of technological electrodes and processes at our companies EPT and TOPAZ. And I would like to thank you, our participants, our people from our project who was devoting themselves to different events, participating in international conferences and giving presentation at international and events, and also participated in secondments during this project. So our project Smart Electrodes, it's coming from multi-scale smart metallic and semiconductor electrodes for electrochemical processing and devices. In this project, we are dealing with mainly with three types of electrodes based on iron group alloys, electrode based on chalcogenides, and so-called technical or technological electrodes developed for electrowinning or electrospark alloying technologies. So our coordinator is Vilnius University, and our project in the framework of Maria Skłodowska-Curie actions, and it's devoted to different types of materials, as I already said. So one of example of these electrochemical devices and one of applications that can be used is catalytic activity of elaborated tungsten and molybdenum alloys, for example, based on iron, nickel, cobalt, and we demonstrated that these alloys can have high catalytic activities for hydrogen production. And of course, there are also some, for example, for electrocatalytic and catalytic properties, there's molybdenum sulfide that will be later Ramunas will be giving the talk about this more in detail. So just to give you, so we have this topic in our project. Also, of course, due to recent events, we could not join in this workshop. Our great colleagues from Belarus was very supportive and was working with this metalluride and obtaining very nice structure, superlattice, they make different conditions to different pulse regimes to find the better deposition for this structure, and these structures are used namely for example, can be used for thermoelectric device fabrications because it's this metalluride. So they did good works, and we had a very nice publication, and it's a pity that because of recent events, European Committee was restricted for the participation of our Belarusian colleagues in the project, but we are really thankful to them. So other topics that I was covering in our project, it was about forms, because it's smart, yeah, so and multi-scale. So we was using not only flat surfaces, but also like we tried to develop 3D surfaces in this project, and for example, like cobalt foam. So in different solutions, we use it different, for example, cobalt chloride or sulfate solutions, yeah, And there it was really different results between them. So in sulfate solution, we have a better 3D structure, or more developed structure, should I say. But nevertheless, with if we added isopropyl alcohol, so we have this nice, in cross section, this nice cobalt forest, how we call it, and it can be used as a 3D catalyst or 3D sensor, or in other different applications. So, and in one of them, it was, we did it and we tried, like, for example, if we use this cobalt form and we modify it by cyclic voltammetry, giving 100 cycles, for example, in hexanoferrite solution, so we can have this modification of this form. And this modified form can be used already as a sensor for detection of chlorine and water. So this is especially taking account EU Green Deal. So this is a good opportunity for green technologies, should I say. Also, we was working with foam, but in another direction, as a Fenton reaction. Fenton reaction, it's a reaction where you're using, for degradation of dyes, we are using iron 2+ ions, and in the presence of peroxide. And we was showing by applying the foam that, for example, if we have iron bar, that it can be minutes and like hundreds of minutes. So like 40 minutes when applying a foam, we already have dealing with seconds. Yeah. So yeah, it's really depending on the structure. And this was also a nice results in our group, in our project. So now, taking into account that yeah, I need to present something about our companies that we have in our project, 2 companies, and one of them is Electronics Perdimo Technologies, or it's Electronics Treatment Technologies. So in our project, this company based in Vilnius, it's dealing with metal recovery of precious or noble metals from electronic waste. And why it's important? Because, of course, again, it's important for rare materials that are, of course, more and more pricey these days. And with the last crisis in Europe, and not only in Europe. So these rare materials are even a bit more costly, I suppose. So in our project, we also with collaborating with EPT company, we was planning, or we was devoting our task to electrowinning. What is electrowinning? Electrowinning, it's recovery of metals. It's the same as electrodeposition. Yeah, when you're using some current or voltage, but already we have a solution like multiple metal ions, and by applying some current or voltage, we can recover these metals from eco solutions. And this is, of course, for electronic waste material. There's several other methodologies that can be used to recover, and they are used for big factories. But here in EPT, the aim was to develop like eco-friendly solutions. This is the first, and to develop technologies that it will be like a smart technology. What I mean is that it will be not a big amount needed, yeah, for treatment. So, and this is, of course, that it's good for logistic point of view. So you don't need to collect like a big, huge amount of waste. Yeah. So And this is also good from CO2 point of view. So you don't need to transport this amount of waste, I don't know, like going from Lithuania to Germany or from Norway. I mean, where you can find these big factories of electronic waste treatment. But by this technology, and that is currently developed at EPT company, you can have these small amounts of electronic waste to be treated. So, but here now, today, I just represent some portion of these results, and namely the influence of 2D and 3-dimensional cathodes in exploring of electrowinning of metals, so-called base metals from electronic based treatment. So this is called like base metals. So the setup was like we was applying really, I mean, high voltages. I mean, not really high, but okay, depending. And it was 60 degrees, and it was 2 electrode systems. And as a cathode, that was all cobalt form. It is, it's not produced by us, but it's a big sheet that was bought from a company, and a stainless steel bar as a reference, yeah, like a 2D material. So, and we performed several analysis to make sure that what we obtain as a deposits. So here I will show you a brief scheme that it's like if you take electronic waste raw, just to give you an idea what you obtain in the end, yeah, it's 1 kilo, and after leaching is a process when you dissolve practically everything, yeah, this waste raw, solid raw, and you obtain some solution where it's base metals, and of course there's also some noble metals hidden inside. So from this solution, part is going for further on for electrowinning, and the solid is going for cells for producer, for example, of copper, because there is a lot of copper here. But if you apply a selective leaching and a reduction process later on, you can obtain like 2, maybe if you're lucky, 5 grams of noble metals. So from 1 kilo, yeah, somewhere around 5 grams. So yeah, the process it's I mean, it's expensive, but not so expensive that to try to buy the new ones that was occurred from nature. So here I present some results about 2 and 3D cathodes, and here you'll see some abbreviation. Just do not mind about this, because it's a different solution containing different leaching metals. This is just acronyms used in the companies, and just to give you ideas that we was using different solutions. So, and from this solution, we obtained the electrowinning process, and we performed the electrowinning process, and you can see that there it was different metals, and these metals was depending, the content depending on the percentage of these metals were used in the solution. But you can see, for example, on 3D cathodes, the plating rate is much higher usually than on 2D cathode. So this is average, yeah. And at 2 volts, yeah. And you can see that the deposits are rather thick or well adhered to the surface, even in foam or in steel. So, but of course, from this solution, this condition was very good to have high extraction or electrowinning rate, but not always the leaching solution was the same. So, for example, in a different solution containing a bit already of iron and different amount of the based metals, so they practically are equal, a bit higher still in some cases, yeah, But for example, for iron, and tin, it's a bit higher because this preferential kinetics probably, but also because you already have not so good adherence from this solution. So it's maybe there's some compounds in this leaching solutions that are preventing to electrodeposit well. And if we are even go higher, because here it was like 2 volts, but even we go higher like 2.5 volts, so you see that it's already like on plate cathode, it's much higher, the deposition rate. It's like, it's sound like nonsense, but yes, it's not nonsense because you have really poor adhesion in the case of foam. So like using 3D electrodes is not always good. So that's why it's research. You also need to take into account that all the conditions like voltage, like the solution, because some of the components of the solution can prevent the good adhesion and good kinetics from this solution. And the third one solution that I want to show here. So this is like already the case when you have equal practically mostly. Yeah, you can see that it's barely in the average. It's mostly equal. So it's again a bit different composition of electronic waste it was, and you have different composition of leaching solution, and of course, deposits are also different. Yes, and as you can see from this solution, we have already very like not uniform, yeah, like with the plate, like lands, small islands or whatever. Yeah, so this was really poor deposition from this solution. So this research performed here show us that we need to really like to take in account like multiple effects of solution, voltage, and electronic waste itself, yeah, because it's giving the composition of leaching solution in the end. Yeah, and yeah, also from if you go to high voltages, even that's also so the same. Yeah, it's but the plating rate is high, so it was 0.3, and now it's like 3 milligrams if you're going to 2 volts. But still from this solution, the coating is really powdery and it's a poor adhesion. So the next, I will shortly present here TOPAZ company, and TOPAZ company it's working with different activities, but the main activities it's with machine tool construction under different technologies, yeah, electrochemical machines and installation like plasma electrolytic polishing machine, electrode discharge machining, yeah. So, and in our project, TOPAZ was in collaboration with us, was trying to assess different coatings by physical-chemical properties and to understand, I mean, how they can be used in their technologies, if what they are producing, yeah, it's a good or not, yeah. So these technologies you can see here, and especially case I will talk here about electrospark alloying. So electrospark alloying, it's a micro arc welding process that uses short duration electrical pulses, yeah. And the application of these technologies is very versatile, from like small parts to bigger parts, even bigger parts, yeah. So it can be even wheels of, I don't know, some really big equipment. And it can be manual, as you can see here, or it can be automatic. Yeah, also you can see the example of the same treatment in TOPAZ. So here's the process. So you apply first, it's a breakdown of inter-electrode gap, yeah, when you're applying pulses. And after this, it's formed an erosion holes and on the cathode and anode. And afterwards, you have this electrode contact moment when you have go with electrode tools to this contact. And after this, it's already formed some surface on cathode. So by applying different electrospark alloying pulses, you can form different surfaces. And this was eventually researched by us, so which pulses are good and which are not, especially for hard alloys that are really difficult to deal with. Yeah, and you can see that really hard alloys, you can have a lot of cracks, but some regimes, of course, I will not show you here, namely which regimes, because it's a company private information. So under some regimes, you can mostly receive less cracking or practical no cracking in the coating. So in this results was good to apply. I mean, they was updating in the TOPAZ this device that owing to these results that we obtained in collaboration with them. So, this technology, electrospark technologies, it's very good to, like, it's shown here, to work with capricious substrates, so like titan or nickel. Or, for example, to apply like very expensive palladium iridium layers, like tin layers, yeah, for example, only to some parts which you need to cover, yeah. And of course, this technique I didn't show here, but we also make a tribological test, and this technique shows that the surface of the work, yeah, of these coatings can be much higher and be resistant. It's higher of these electrospark alloying pieces, and it's a really good technique, especially if you need, for example, sorry. To make out in field, yeah. For example, some machine is broken in the field, and you need to repair it there, not taking into the lab or to the company. So also some of the results was good for them to upgrade an equipment for electrochemical complex, which is applying protective coatings made of durable insulating material. So they also was able to upgrade some of the regimes. So this was what I was shortly was talking and presenting some of our results. And of course, thank you for your attention, for your presence today, supporting our workshop and supporting our projects. Thank you again.
Thank you. Thank you for nice talk.